Okay, hello everybody. The speaker today of this new webinar is Christphe Hazard. Christphe Hazard is a senior scientist at the French National Scientific Research Center, CNRS, and at Institut Polytechnique. His research topics are on spectral analysis of scattering problems, on artificial boundaries, waveguides, harmonic waves, transient waves, and coupled phenomena. And today, the talk is about the spectrum of cavity containing a negative material. Thank you, Christphe, for accepting our invitation, and please, you can start your talk.
Okay, thank you very much.
Okay, I forgot just something to say, that Christphe is a friend of more than 30 years.
So thank you very much, Nabil, and thank you for this kind invitation. Maybe I could say first that do not hesitate to stop me if there is a question, if there is something which is not clear. Maybe it is simpler than waiting for the end of the talk. So do not hesitate to stop me if you have a question. So the subject of my talk today is about those very well-known materials, often called metamaterials, and they have been the subjects of a huge amount of articles in the, let's say, 20 years, last 20 years. And here I'm going to speak about a joint work with my PhD student, Sandrine Paolo Antoni, who defended her thesis about 3 months ago. And that's about the question of a spectrum of a cavity containing such a material. So, what is a negative material? This notion appeared in the context of electromagnetism. And in general, we call a negative material a material for which the electric permittivity, or at least the real part of the electric permittivity, or the magnetic permeability, mu, or at least its real part, or both quantities become negative. And this may happen only in some frequency range. This means that these quantities, epsilon and mu, necessarily depend on the frequency, which is denoted here by omega. It is a dispersive material. And the question I am interested in here is very simple. You take a cavity, a closed cavity, and you put some negative material inside the cavity, and I want to know what is the spectrum of such a cavity partly filled with negative material. So that's the question I'm going to speak about. If you have only one idea to remember from my talk here, it is the fact that contrary to the case of a cavity filled by a usual material, usual dielectric material, or just say vacuum, we know that the spectrum of the cavity is purely discrete. Here, we are going to see that the presence of the negative material generate an essential spectrum, and this essential spectrum is related to various unusual resonance phenomena. And I first recall what is the discrete spectrum. The discrete spectrum here is the set of isolated eigenvalues of finite multiplicity. And the remainder of the spectrum is called the essential. And this essential spectrum may contain two kinds of things. You have on one hand the limit points of the spectrum, accumulation points of the spectrum, and on the other hand, you can have isolated points, but these isolated points are necessarily eigenvalues of infinite multiplicity. So that's the essential spectrum, and I'm going to show now how this essential spectrum appears. I'm not going to speak about Maxwell's equation. I'm going to speak about a very simple two-dimensional scalar equation, which consists in finding the resonances of, let's say, acoustic cavity here, since this is a scalar model. Acoustic cavity, two-dimensional cavity, which will be denoted by C. And my cavity is composed of two parts. P and N. P is for the positive material, ordinary material, and N for the negative material. And my resonance problem here consists in finding some complex frequency omega and some function phi, which is a non-zero function, which satisfy this Helmholtz-type equation here, which involves two coefficients, alpha omega and beta omega. I will give some details about them after. And I have here a boundary condition. I choose here a Dirichlet boundary condition on the boundary, but I could have a Neumann boundary condition or Robin boundary condition. It does not matter here. And about these coefficients here, alpha and beta, I will assume in all my talk that there are piecewise, for a given frequency omega, there are piecewise constants in the cavity. In the positive material, in P here, they take two positive values, alpha P and beta P. And in the negative material, they take some values which will be denoted by alpha N and beta N, and they depend on omega. So I put the omega in the index here. And this value may become negative in some frequency. So that's the problem I am interested in. And I just have to mention that this equation here is a condensed form for writing actually two Helmholtz equation. One Helmholtz equation in P with this coefficient here, and another Helmholtz equation, which is the same, but with the alpha and beta replaced by these alpha n and beta n. And these two Helmholtz equations are coupled by transmission condition along the interface between the two media. And this transmission condition says that I have the continuity of phi and the normal derivative of phi divided by this alpha omega here. And of course, in general, this is a nonlinear eigenvalue problem since omega appears here, but also in the coefficients alpha omega and beta omega. So let's say a few words about the several references, and first the pioneering mathematical studies for that dates back from the work by Costabel and Stefan, and they were actually the first who exhibited the fact that the role of the contrast is the ratio between the coefficient alpha in the negative material and this coefficient in the positive material. And they showed that not in the context of cavities, but for scattering problems, they showed that when this contrast is equal to -1, this is a critical value in the sense that the scattering problem becomes ill-posed, whereas it is well-posed when the contrast is different from -1. So they were the first to show the role of this critical value. And a bit more than 10 years later, Dauge and Texier showed that in the case of corners, the result by Costabel and Stefan was for smooth boundaries. And in the case of corners of the interface, this critical value becomes a critical interface and critical interval, sorry. And we are going to see that a bit later. And during the same period, this was actually the beginning of a long story which began at my laboratory poems, a long story of various theses, the theses of Karim Ramdani, of Lucas Chenel, of Camille Carvalho, who were supervised by Anne-Sophie Bonnet and Patrick Sierlet. And these theses were about negative material and in particular about the so-called T-coercivity technique, which puts a new light on this critical value and this problem of negative material. And if I put these references in yellow here, that's just to say that all my work with Sandrine Paolantani and all the content of my talk today is based on their work, on this work and this long history work which goes on now at Poems. There are a huge number of other articles, and here I give some references. The negative material are used for studies about cloaking, about also the Neumann Poincaré operator. There are lots of articles about this operator, which is the operator which appears when you look at the low frequency, the so-called quasi-static approximation of the equation I'm interested in. And when we look at that from the integral equation point of view, this Neumann Poincaré operator appears in this context. I also give the reference for two very beautiful articles about indefinite Laplacians. And these articles study the properties of the operator I mentioned before, exactly for the critical frequencies, the critical value of the contrast. And there are very few numerical studies for the calculation of a spectral property of a device containing a negative material. And I just here cite the work from friends of Marseille in the south of France about photonic crystals. Okay, there are huge references, and I just give some examples here. So the outline of my talk today is very simple. I'm going first to say very simple things about homogeneous cavities, and then I will speak about non-homogeneous cavities, and I will finally conclude. So let's see what happens in homogeneous cavities. So the message here is the following. I'm going to show you how the knowledge of the spectrum of a usual closed cavity filled by a positive material, a homogeneous positive materials, gives you the spectrum of a cavity filled by any negative material. That is very simple to see the link between both problems here. So to show that, I have to recall some simple things about the case of a cavity filled by a positive material. So now I assume that my coefficients alpha and beta are equal to alpha p and beta p, which are constant functions in the cavity independent of omega. And in that case, my nonlinear eigenvalue problem simplifies into the linear eigenvalue problem, which is shown here. Just my Helmholtz equation in the whole cavity. And if I denote by lambda of omega this quantity here, this means that my the value omega is the resonance of the problem if and only if this lambda of omega is in the spectrum of the Dirichlet-Laplacian minus Dirichlet-Laplacian here. And of course, this is very well known thanks to a compactness property, which is valid if the boundary of the cavity is regular, is smooth enough, let's say a Lipschitz boundary. We know that the spectrum here of the Dirichlet-Laplacian is discrete. It is purely discrete. It is composed of a sequence of positive eigenvalues, finite multiplicity, which tends to plus infinity. So that's a very simple situation. And in particular, many of you probably know that if I consider the case of a rectangle cavity with lenses L1 and L2, that's a very easy exercise to see that using separation of variable, the eigenvalues and eigenvectors are given by this formula. For the eigenvectors, you have a product of sine functions, and the eigenvalues are given by this formula, where n1 and n2 are two positive integers. If I say that, it is just to understand that in that case, I obtain what I call bulk resonances, because this function oscillates in the whole cavity, not only near the boundary or something like that. These are bulk resonances. And in general, the solutions to such an equation leads to bulk resonances. So what about homogeneous cavities filled now by a negative material? In that case, if I assume that my coefficient alpha and beta are given by my alpha n omega and beta n omega, which now are constant in C but may depend on omega, my nonlinear eigenvalue problem simplifies into the same as in the preceding slides, but now the definition of my lambda omega, of course, has changed, and it is slightly more complicated, but the fact that omega is a resonance is again equivalent to the fact that lambda of omega is in the spectrum, the purely discrete spectrum of minus the Dirichlet-Laplacian. This means that if I want to find the spectrum, the resonances of my cavity, I just have to find the inverse image by this function lambda of the spectrum of the Dirichlet-Laplacian, and the modes, the resonance modes associated with these resonances are, of course, the associated eigenfunctions corresponding to the eigenvalues of the Dirichlet-Laplacian. So to see how to construct this inverse image, of course, I have to give you some details about these functions, alpha omega and beta omega. And there are several models of negative material. And the first one here is the simplest one. It is the so-called Drude model. And the simplest case is the non-dissipative case here. And in this case, the function alpha or the function beta, here I choose alpha, but it would be the same for beta, of course. The function alpha is given by this formula. I have here alpha p is a positive coefficient, and here I have this function here where omega alpha is often called the plasma frequency of the Drude model, of the Drude material. And you see this function is represented here. You see that this quantity becomes negative if omega is smaller than this plasma frequency. And I see that for the when omega is equal, when omega squared is equal to omega alpha squared divided by 2, I obtain exactly -1 here, which is exactly the critical value of the contrast. We will go back to this critical value later. So in that case, in that simple case, when beta is a positive number, my function lambda of omega is simply given by this formula. So as it is a linear function of omega squared, which is represented here. And so if I want the inverse image of the spectrum of minus the Dirichlet Laplacian, I just have to put my eigenvalues here on the y-axis, and I obtain the values of omega squared here, which are indicated by red points. So that's very simple here, because lambda of omega is the linear function of omega squared. And we see that in that case, there is nothing really interesting. We have an accumulation only at infinity. The more interesting case is what I call here the double Drude model. Double because I assume that alpha and beta are both satisfying a Drude law. So alpha n is defined by this here with the plasma frequency corresponding to alpha, and beta is the same with an omega beta here. And in that case, my function lambda of omega is given by this formula. And what you see in this formula is that when omega is close to 0, lambda of omega tends to plus infinity. And this function is represented here with respect to omega squared. And if I want the inverse image of the spectrum of the Dirichlet Laplacian here, I put my eigenvalues here, and you see that for each eigenvalue, I will obtain two values of omega squared, one value near 0 and one value which will tend to infinity, where the eigenvalue lambda here will tend to infinity, whereas the eigenvalue here close to 0 will tend to 0. So in that case, I obtain some accumulation at infinity, same as before, but I also obtain an accumulation near the frequency 0. Other kind of model, this is the dissipative Drude model. In the case where this model is, the material is dissipative, I add here a coefficient gamma alpha, which is a damping coefficient here. And in that case, so my omega squared in the model, in the non-dissipative model, is replaced by this quantity here. And we see that lambda of omega is given by this formula, which shows that I will obtain an accumulation of resonances, again, of course, at post infinity, but as well as at the pole of this function here, that is at minus r gamma alpha. Okay, in the case of a double Drude material, double dissipative Drude material, if alpha and beta are given by similar laws here, I will obtain accumulation at the both poles, of course. And so on and so on. I just give some other model, which is often called the Lorentz model. The Lorentz model, the negativity property of the material occurs not at 0, but near a frequency, which is denoted here by rho alpha. And this rho alpha is often called the resonance frequency. And you see that this function, this law for the Lorentz material, which is indicated here, gives you a negative material for omega when omega squared is contained in this range, in this interval here. In this case, lambda of omega is given by this formula, and I will obtain an accumulation of resonances near the pole rho alpha. And I have also a similar model for the dissipative Lorentz model, where the denominator has to be replaced by this formula here, where I have a damping coefficient gamma alpha. And in that case, I will again obtain an accumulation of resonances near the pole of this function here. And the most general case corresponds to what we can call here multiple pole contribution, which consists actually in a sum of single poles, Lorentz contribution poles of this form here. And in that case, I will have an accumulation at each pole of my Lorentz function indicated here. So the message we can remember from these homogeneous cavities is that there is some essential spectrum in homogeneous cavities filled by a negative material. This essential spectrum is composed of limit points of eigenvalues at the poles of this function alpha or beta, and it is associated to highly oscillating bulk resonances. These are bulk resonances, as I said before, because these are simply the bulk resonances of a homogeneous cavity filled by a positive material. And of course, this corresponds to high oscillation because they correspond to the case of high frequencies in the case of positive material. But now for negative material, I see these highly oscillating resonances for omega close to a finite frequency. Okay, that's all what I will say about homogeneous cavities, and let's go now to the case of non-homogeneous cavities. And I'm going to work with a very famous French cavity, which is Camembert cavity. Here you can imagine famous cheese in France. And you imagine that I have a portion of Camembert here, which is my negative material. And I'm going to see what are the resonances of such a cavity here. So I recall my problem here. I want to find complex values of omega. And the function phi, which is supposed to be in the subpolar space H10 of the cavity, non-vanishing function, which satisfy my Helmholtz-Strip equation here. And my boundary condition is contained in the definition of H10, of course. And here I'm going to consider the case of the double Drude model, that is the case where alpha and omega in the negative material satisfy the Drude law here. So the alpha p and beta p are exactly the values I have here in the positive material. So I have two constants here which define my negative material, omega alpha and beta, and omega beta. The basic ideas for finding the resonances of this problem is first to linearize the nonlinear eigenvalue problem, and I will show you that by an augmented formulation approach, we can do that. And this augmented formulation approach consists in introducing an auxiliary unknown, which will be denoted by U, which allows me to transform this nonlinear eigenvalue problem into a linear eigenvalue problem for the pair phi u here. And in addition, I will show that, well, we will see, I will not give the proof, but we will see that A is a self-adjoint operator. And once I have done that, I will find the essential spectrum of A by means of Weil sequences. What is the Weil sequences? It is a way to characterize essential spectrum, and we know that a value omega squared belongs to the essential spectrum of my operator A, if and only if we can find a sequence where I will denote by xn the pair phi n un, such that I have these three properties here. The first one is simply the fact that I choose a normalized function here in the Hilbert space in which A is self-adjoint. The second property says that this sequence satisfies the usual relation of an eigenvector, but asymptotically when n tends to infinity. Actually, these two conditions give a characterization of any point of the spectrum. And the last here is specific for the essential spectrum. It says that xn must tend weakly to 0. And the advantage of these veil sequences compared to other characterization of the essential spectrum, such as the Fredholm-Ness property, for instance, is that veil sequences inform us about the nature of the resonances. They give us the physical nature, the way how the medium resonates. Actually, we just have to look at what kind of xn it is. So let's begin by the first step, linearization. Here, I assume that omega is different from 0 and omega alpha. And if you remember, at 0, the values of alpha, omega, and beta omega tends to infinity. So I exclude that. And for omega alpha, the values of alpha omega is 0. So this ratio tends to infinity. So I exclude this singular value, the singular values. And in that case, I just replace alpha omega and beta omega by the expression, the explicit expression, and I obtain this new equation here, which is written simply the same as before, but more explicitly. And you see that omega appears here and here. In this equation, I did not say, but 1n is simply the indicator function of n, which is equal to 1 in n and 0 in p. And so omega, the nonlinearity in that case is due to this ratio here. So the idea of a linearization is simply to choose that as an auxiliary variable. And to do that, I just need to introduce some notations. I denote by R the operator of restriction from C to N. That is, when you take a function defined in a whole cavity, you take its restriction to the negative material, and R star is the adjoint operator. It is simply the operator of extension by 0 from N to C. That is, you have a function which is defined in N, and you extend it by 0 in the positive material, in P. And as I said before, my auxiliary variable is simply to take the restriction of this quantity to the negative material. So I define U as the restriction of a gradient of phi times this ratio here. And when we do that, this equation simply becomes this equation here, which is linear with respect to omega squared. And the second equation here is simply the definition of U, which is rewritten by putting the omega term in the right-hand side. And you see that the omega is involved it appears only on the right-hand side here. The left-hand side of the equal signs do not, you do not have omega here. So my problem is linearized. And to sum up, if omega is different from the singular value, then the function phi is solution to my nonlinear eigenvalue problem, if and only if the pair phi u, which belongs to H10 for phi and L2 for u, this is simply the gradient of phi taken in n, so L2 squared, of course, satisfy this linear eigenvalue problem where A is defined by these quantities here, which are simply the left-hand side of my previous equations. And it is easy to see that this A defines an unbounded, non-negative, self-adjoint operator, provided that you choose for the Hilbert space L2 for phi, L2 for u, and you choose properly the coefficients of the inner product for this Hilbert space, and the domain of this operator is simply chosen such that both quantities here.
You have on the chat from.
I can't see the chat. If you can read it.
Okay.
Because I have my full screen.
He asked you if the divergence of RU is well defined. He asked if there is a gap.
Yes, this is a good question. That's why I read that in this form here, and I do not separate both parts, because yes, he's right, that there is R star U is 0. This is 0 in the positive material. So there is a gap, and it may be not in L2. But the fact that I choose a domain by imposing the fact that this is in L2, there is no gap for the quantity here, gradient phi plus. So there is a relation between the normal traces of phi and the normal trace of u here.
C'est bien rattrapé, no problème.
C'était pas Belassen.
C'est parfait.
Okay.
J'étais très inquiet. The interface is smooth.
Don't worry, be happy.
Okay, no, the interface is smooth between the two domains, the two parts of the domain.
Yes.
Okay, thank you. Excuse me.
Yes. Okay, so I know that this operator is self-adjoint and non-negative. This means that the spectrum of this operator is positive and real. And so now I'm going to look at the essential spectrum, and to understand the formulation of the result, I just recall the definition of the contrast, which is denoted here by kappa omega. I recall that this is the ratio of the value of alpha in a negative material by the value of alpha in the positive material. This is this simple function here, which is negative below the plasma frequencies. And the main results are represented in this picture here, where the discrete spectrum is represented by blue points. I will not say anything about that. I'm interested in the essential spectrum. And you see that the essential spectrum, which is represented in red here, consists of 3 parts. You have 2 points at 0 and omega alpha, which are the bounds of the negative interval here. Here it corresponds to the contrast, which is equal to -infinity, and the plasma frequency corresponds to contrast, which is 0. And at the middle here, we have exactly this singular value -1, this critical value -1 of the contrast. And we have, in addition to this value, we have an interval which is centered at this value. And actually, this interval depends only on the angle of the portion of negative material, and I can show that now. If you take a very small portion of negative material, so a very small angle, you will have an interval which is nearly the whole interval between 0 and omega alpha squared. If you increase the portion, increase the angle, then this this interval decreases until you reach the situation where there is no corner, and in that case there is no interval. You just have one singular point at the middle value here of the interval corresponding to the critical value -1. And then if you increase again the angle, you see that the interval increases again until it reaches nearly the whole interval between 0 and omega alpha squared. Actually, you have a symmetry with respect to this situation where there is no corner here. And what is really interesting is to see what kind of resonance phenomena is associated to these different parts of the essential spectrum. First, for 0, actually, I will have exactly the phenomenon of resonance which I talk about in the first part for homogeneous cavities. We have in that case an accumulation of eigenvalues, accumulation of the discrete spectrum near 0. And this, I'm not going to speak about that because in that case, the veil sequences are constructed using the eigenfunctions of the cavity exactly as in for a homogeneous cavity. So that's not really interesting. I do not speak neither of this value, which corresponds to a divergence-free function, which is close to what happens for Maxwell's equation. So that's a different phenomena which appears here. What is really interesting here is the fact that this middle value here corresponding to the contrast -1 is associated to surface resonances. That is what we call surface plasmons, which are waves which are localized near the interface, whereas the interval on both parts here correspond to what we call a black hole phenomena. These are corner resonances, and I will say a few words about that in the end of the talk. So I'm going to show now how to construct these veil sequences for these two kinds of resonances. So first, the case of surface plasmons. So I'm interested here for this particular value. And in that case, as I said, I can have localized waves which are highly oscillating near any point of the interface between the positive and the negative material. And this point, as I said before, is related to the contrast -1, which was exhibited by Costabel and Stefan, and who showed that the time harmonic problem is ill-posed in that case. And how do we see that? That's very simple. We just have to use separation of Cartesian coordinates by considering a rectilinear interface between two half planes. So here I forgot my camembert, and I assume that the negative material fills a half plane corresponding to x1 negative, and I have a positive material corresponding to x1 positive. So I consider my equation here where I remove the second term here, and actually this second term is a compact perturbation of the first one. And when I am interested in the essential spectrum, compact perturbations are not really important. So the important term is this one. So I want to solve this equation, this simplified equation, for the particular case where alpha omega correspond to the contrast -1, that is, it is equal to minus alpha p in the negative material and plus alpha p in the positive material. And in this case, it is obvious to see that the solutions are given, the separated solution, separated variable solution are given by this simple exponential for any real value, positive real value of k here. These are surface waves in the sense that they are oscillating in the x2 direction and exponentially decaying in the x1 direction here. Since I have a family of solutions, I can take any superposition of this family of solutions. So I can take a function f, let's say a smooth function, compactly supported, and I will obtain another solution of my simplified equation. And using the usual properties of Fourier transform, I see that this function actually is a localized surface wave because it is localized in the x2 direction. It was already localized in the x1 direction. And if instead of choosing one function f of k, I choose a sequence of function f of k over n, it is easy to see with the simple change of variable that it amounts to replacing x1 and x2 by nx1 and nx2, which means that I just compress this localized surface wave. I compress it by a factor n here, which means that I can construct localized, highly oscillating surface wave as n tends to infinity. And so how can I construct various sequences for that? If I denote by psi n my function here, I use that phi n for constructing various sequences in a very simple manner. You choose your origin or on one point of the interface between the negative and the positive material. You choose x2 along the interface, and you just truncate that psi n by a function, a smooth function, which is compactly supported near a small vicinity here of 0. And you take for xn the value, this function phi n here, and the un, which corresponds by the auxiliary variable formula. So I do not show again this formula, but in that particular case, it corresponds simply to taken -2 times the restriction of the gradient of phi n. And in that case, it is easy to see that this is a veil sequence for this critical value corresponding to the contrast -1. Okay, so that's it for the contrast -1. And what about the corner resonances? So what about these two intervals which are located on both sides here? The idea here is the fact that we can have black hole waves. And what are these black hole waves? These are waves which have oscillations which are we have more and more oscillating functions near the corner where the velocity tends to 0 near the corner. This means that when this means that actually the wave goes towards the corner but never reach it, and actually the energy of the wave accumulates near the corner. And these black hole waves can occur if kappa omega belongs to a critical interval that only depend on the angle of the corner. And I give here the case of a right angle. In that case, the critical interval is the interval -3 -1/3 without the critical value -1. And for our Drude model, this critical interval of contrast corresponds exactly to the critical interval given by this formula, but that's what I showed on the picture showing how this interval depends on the angle. So how can we construct veil sequences in that case? For that, we have to do a very similar technique for finding these black hole waves. We are going to use now separation of polar coordinate by considering now an infinite portion of negative material here, and I still consider my simplified equation by removing the second term here. And using separation of variables of polar coordinates, I obtain what I call my black hole waves here, which is the product of a function of r by a function m of theta, which is, I don't give the expression for this, but it can be shown explicitly with sine functions. But what is important here is the dependence with respect to r. And if I write it as an exponential, you see that when r tends to 0, this function becomes more and more oscillating. Because eta here is a positive number which range from 0 to plus infinity, when omega ranges from the ends of the interval towards the center of the interval. And I have here a picture showing this function. You see that the oscillations are more and more rapid near the corner. So how do we use this black hole wave for constructing Veil sequences? That's quite simple, but the simple but not obvious. The natural idea would be to truncate this black hole wave near the corner and close, doing a truncation which is closer and closer to the corner. It cannot work, and actually we can show that this is impossible to use this technique. What we are going to do is to use the black hole wave near some given, when I look for a Veil sequence for a given omega, let's say omega star in my black hole interval, I'm going to use a superposition of the black hole wave in the vicinity of this particular value. And to do that, I use a sequence of functions such as this one here, which simply tends to a Dirac at this particular value, omega star. So I take a smooth function compactly supported near 0, and this sequence of function tends to a Dirac. And for my xn here, I choose my black hole wave and the auxiliary variable u associated to this black hole. Of course, this superposition is not compactly supported, and I need a truncation function so that it can satisfy the boundary condition on the boundary of my camembert here. And once I have done that, I can show easily that this function, this xn, renormalized is a Veil sequence for this particular value of omega. Okay, that's it. So I can conclude by just saying that I have presented here the simplest case corresponding to a Drude material for a simple domain. We have the same kind of results for polygonal domains. We have studied also the case of smooth curved interfaces, and we have similar results, but the technique is far more complicated in that case in order to construct explicitly those Veil sequences. We have worked also with the dissipative Drude model as well as the dissipative and non-dissipative Lorentz model, and we have exactly the same kind of results. What is important here is the fact that these different parts of essential spectrum appears from the same critical values or interval of the contrast. There are some perspectives which concerns 3D scalar problem, and now there is thesis on this subject by Maran Riani now at Poems. Maxwell's equations too are quite interested to study. One real question is the case of curved corners, where you don't have a straight corner, but the the corner correspond to curve lines. And the real open question I want to mention before ending is what I call here the mystery of the nonlinear spectral problem. And to say it very shortly, the idea here is that it seems impossible to define actually a proper notion of essential spectrum for this nonlinear problem. It is easy to see that we can speak about eigenvalues for the nonlinear problem, and they correspond exactly to the eigenvalues of my linear eigenvalue problem. But for the essential spectrum, there is a mystery about the correspondence between essential spectrum of the nonlinear problem and the linear problem. So I stop here, and I thank you very much for your attention.
Thank you, Christophe. Is there some questions?
Oui.
Okay, go on.
Thank you, Christophe. It was very interesting, really. I have first a question. Can you please go back to the slide where you consider the simplified equation here? This one.
This one, for instance.
Yes. Exactly. Just to understand, you actually you forgot about this term because of compactness.
Because of compactness, I mean, yes. The argument is that it does not matter as far as I consider veil sequences.
Okay, exactly, because you use it for this.
Yes.
You have a weakly convergent sequence, and you can yes. Forget about this.
Yes, exactly. Because actually, this quantity, when I look at this quantity for the veil sequences, it tends to 0 in L2. What exactly. Is important is the gradient. The gradient exactly. Does not tend to 0.
D'accord, exactly. D'accord. The second question, the last slide, please. You yes. just picked my question. What is the obstruction to obtain some results in dimension more than 2?
That's the 3D scalar problem, you mean?
Yes.
The difficulty is to find the black hole waves in that case, because there are some studies in the case of a conical corner. You have a conical corner with a symmetry of revolution along an axis. And in that case, this is not really a 3D problem, but in general, the problem you have here to solve the problem, when you have a separation of polar coordinate here, you obtain a problem how could I explain it? You obtain a problem in R and in problem in theta by using a separation of variables from this problem. And the problem in theta is not usual. It is an ordinary differential equation in 2D, and we can solve it by hand. It is very easy. But when you look at the problem in 3D, it is a problem of where you have two Beltrami Laplace-Beltrami operator, but one with the plus sign and one with the minus sign, and we do not know anything about that, and that's a real question. We do not hear you, Belsen, faut tu mettre ton micro.
Sorry, excuse me, because this problem, you don't need to go to 3 space dimension. This problem you are talking about arises even if you try to change variables in 2D dimensions.
Yes.
You see, if you change, if your Laplacian becomes with variable coefficients, we have the same difficulty.
Yes, exactly. But the advantage of the 2D is that you have ordinary differential equation and you can solve it. You have an explicit solution. In 3D, you do not have the explicit solution.
It's technical, it's very nice, really. Merci beaucoup. Très bien.
You're welcome.
Do we have other questions? Okay, thank you very much, Christophe, for this very beautiful talk. And,
thank you.
And I hope we will have you again. Okay. Merci, Christophe.
Eh bien, merci à vous. Thank you very much, everybody.
Merci.
I can stop. Voilà.
Allez, à bientôt.
À bientôt. Merci beaucoup, Nabil.
Au revoir, Christophe.
Au revoir.